Hey everybody. Today's lesson is the first lesson in Unit 1 for pre-calculus functions and graphs. Today we're going to talk about some of the basics for functions, including finding domain and determining whether a relation is a function or not, using function notation. So a relation is a set of ordered pairs. So any x and y, but a function is a special relation between two variables so that each value of the independent variable that we call the domain, there corresponds exactly one value of the dependent variable, and that's known as the range. So a set of ordered pairs is a relation, and each x has to have a unique y in order to be a function. So let's get started here. We want to determine whether each relation below represents a function. And you can see that there is a domain of 2, 3, -1, and 2 again. So this becomes an issue because we don't have unique x's. 2 is repeated. That would make this just a relation. And we could say the reason for it just being a relation is because 2 maps to two different y values. When x equals 2, maps to two different y values. And if you remember from Algebra 2, this relation would fail the vertical line test because 2, 5 and 2, 3, 2, 5 and 2, 3 fail the vertical line test right there. Now in this next example, the area of a circle is a function of the radius. So if you think about the area formula, area is pi r squared. That means the radius is the key factor here. And area depends on the radius. So this is definitely a function in terms of radius. This is a function. So it's a relation, but it's also a function because a function is a special relation. On part C, we have a list of friends and then the birthdays. So you see Ruth Ann and Sean both share April 13th. But that's still going to be a function because every input is unique. Our input is the list of friends, and the output would be the birthdays. And we would say something along the lines of every input is unique. It's okay for a function to have the same y value with different x values. So two friends can share a birthday. That would mean that their output is the same, but the input is a unique value. And in this case, let's see, -2 maps to -1, 1 to 4. So each input is matched to exactly one output. This would be a function. Every input is matched to exactly one output. Every input is matched to exactly one output. So it too is a function. In our course, we need to be able to recognize symbolic representations for functions. So when you see this symbol, f of x, we read that f of x, or f is a function of x. The letters F, G, and H right there in the middle of the alphabet are used to name functions. And f of x equals y is the value of the function at a particular x. So when you read the f of 2 is 9, that simply means that the point 29 is on our graph. Now in Algebra 2, we represented functions using tables, graphs, mappings, equations, and verbal descriptions. In pre-calc, we're going to expand on that knowledge and use what the Harvard Calculus Consortium developed called the Rule of 4. And the Rule of 4 will help us strengthen our mathematical understanding as we move through the year. It's the basis for our calculus course. Now the Rule of 4, I like to use the mnemonic GNAW, G-N-A-W, because it's easy to help me remember. G for graphically, N for numerically, A for algebraically, and W for words or verbal. We need to be able to go back and forth and interchange between the 4 different representations. If you have a graph, can you write a table? Can you turn the graph into an algebraic equation? Can you describe the graph verbally with your words and analyze that graph? Each of us should find a strength in one of those 4 areas. So using function notation, we're going to use the equation 2x squared minus 3x to evaluate the f of 2. So the f of 2 simply means that I want to substitute the value 2 for my x variable. In place of x, I'm going to put a 2 in each situation and then simplify by evaluating. So this is 4 times 2. That's 8, and 3 times 2, that's 6, and 8 minus 6 is 2. So the ordered pair 2, 2 is on the graph. I said 2, 2. Then f of x plus f of 2, we just found the f of 2 is 2, and f of x is this function here. So the f of x plus the f of 2 would be 2x squared, would be 2x squared minus 3x plus the f of 2, which is 2 over here. So that was pretty simple. I'll try a little bit more difficult one. Okay, the f of 2x, we had 2x squared minus 3x, and in place of the x, we're going to substitute 2x. And then simplify and evaluate. So this is 2 times 4x squared minus 6x. So the f of 2x is 8x squared minus 6x. And then the f of x plus 2, I think I have this out of order on my slides. You have the opposite. This is your letter D. So the opposite of f of x would be the opposite of the function 2x squared minus 3x. Distributing the negative to both terms would be positive 2x squared plus 3x, and this is your letter D. Then your letter E is the f of negative x, or I would rather say the f of the opposite of x. So in place of our variable x, in each case, we're going to substitute the opposite of x, or negative x. And if you square a negative number, you'll end up with a positive. And then in this case, a negative times a negative is a positive. So we get 2x squared plus 3x. And then your letter D, E, your letter F, I believe, is this one back here. X plus 2, this is your letter F on our notes. So we want to do 2x squared minus 3x, and in place of x, we have this expression, x plus 2. In the first set, we want to expand that binomial by squaring it. That's x squared plus 4x plus 4, and then distribute the negative 3x minus 6. Then using distributive property here, we have 2x squared plus 8x plus 8 minus 3x minus 6, and combining like terms, the 8x and the minus 3x will give us 5x, and then 8 minus 6 is going to produce 2. So letter F is 2x squared plus 5x plus 2 when we evaluate the F of the quantity x plus 2. And then letter G is another binomial, so 2x plus h quantity squared minus 3x plus h. Then doing the same thing, if you want, you can turn the video off and try this on your own and come back to check your work when you're finished. So what I did is expand that binomial, x squared plus 2xh plus h squared, and distribute the negative 3, and then distribute the 2, and from there were no other common terms that we could collect terms for. This should have been your final answer. 2x squared plus 4xh plus 2h squared minus 3x minus 3h. Now you want to note that because on letter H, this answer we just got is that right there. And then we want to subtract the function. So we have 2x squared, excuse me, plus 4xh plus 2h squared minus 3x minus 3h. This is our f of x plus h. And then we're going to subtract the function. So the function is 2x squared minus 3x. And then divide that by h. This is called the difference quotient. And the difference quotient we'll find has many applications in calculus. Okay, so distributing here would give us a couple of terms that we could eliminate. So negative 2x squared and positive 3x, all divided by h, would eliminate the 2x squareds and the negative 3x. And then you notice each term left has an h in it. So if we factor out an h from the numerator, we could divide out the h in the denominator, and then the difference quotient result is 4x plus 2h minus 3, called the difference quotient. Okay, just a few more. Implicit and explicit form. When we have a function defined by an expression in x and y, we say that it's given implicitly. So an example of an implicit equation would be something, say 5x squared minus 2y cubed equals 4. That would be implicit form. And when we solve for y in terms of x so that y is isolated, that's called explicitly stated. So an example of an explicit function would be something like this parabola. So we will work with implicit functions and explicit functions in our course. So looking at this equation, we want to solve each for y in terms of x. This one's going to give us a line. And I want to know, is this a form of a function or not. So I would say yes, it is, because it is linear in its form. This is a linear equation. In this case, if we bring the y term to the other side and the 3 and isolate y, we have 1/2 x squared minus 3 if you leave it in that form. And that is definitely a function because it's a quadratic or a parabola. On part C, x times y equals 1. So y is 1 over x. Now we can't have division by 0 in our domain, but 1 over x is still a function. It's a rational function. And if you recall from Algebra 2, that graph has a branch here in quadrant 3 and a branch here in quadrant 1. So it definitely passes the vertical line test and is a function. This one is going to not be a function since solving for y causes us to take both the positive and negative square roots. When we're doing the operation, we have to square root both sides. We introduce that square root, so this one is not a function. It's only a relation. And if you remember your geometry, this is an equation for a circle centered at the origin with a radius of 2. So not a function, fails the vertical line test. If a function is defined by an equation and no domain is specified, then we have to think about the largest set of real numbers that's going to give us a value for y, which is also a real number. Some of the things that cause problems are division by 0 or getting a negative square root or a negative fourth root, any even root of a negative number that would cause an imaginary number in the domain. So we have to consider those cases. Let's look at a few of them. In example 4, find the domain and the range in each of the relations. In part A, the domain would be 8, -2, 1, 8, 2. You notice I'm looking at each x term or the input value. The range would be the output or the y values, 3, 8, 6, and 7. In this case, the domain is the input on the mapping, 5, 0, 2, and 4. And the range is the output. And even though 1 maps to 2 different numbers, we only have to list that value one time. You don't have to write 1 twice. Okay, so we have a table of values, we have a mapping, those are multiple representations. In part C, that's a graph, it's a continuous graph. Using some maybe new vocabulary, it is a function since it passes the vertical line test. The domain is all real numbers, so -infinity to +infinity. In the range, starting at the smallest number for -infinity and stopping at the largest y value, including 2, since that point, -1, 2 is part of our function. We're going to bracket the range. And then letter D, this is not a function, it's a relation. This one is called a discrete set of points. It's discrete, they're not connected. It's not a sideways parabola, it's just a discrete relation, not a function. And the domain would be all of our x values, -3, -2, and +1. And the range will be -3, -2, -1, 0, and 1. So that's pretty easy. I have a couple more examples. On this example, we want to find the domain of each of the following functions and then use a graphing calculator to verify our findings. So in this case, it's not a circle because there's no addition. And if you saw conic sections last year, this one is going to be a relation only. And it's going to be a hyperbola because there's subtraction. So just really quickly, I'm going to draw the little box around where the branches go. Create those asymptotes. So the function itself, or the relation, I should say, it fails the vertical line test. It's got a little parabolic shape on the right at +3, and another one on the left at -3. It's a relation only. The domain includes -3 and includes +3, but none of the values in the middle there. So this is a relation only, not a function. The next one, well, that's very familiar. So if we factor the parabola and solve for 0, we have a 0 at 0 and another 0 at -4. And if you take half of the 4, that's at -2. And substituting the f of -2, you know what I'm here. I shouldn't rush. The opposite of b over 2a is the axis of symmetry, and our b is 4. So the opposite of 4 over 2 times 1 is -2. And if you substitute -2 in here, we've got 4 minus 8 or -4. So there's our vertex. And our parabola. Uh-oh, something went wrong. Let's try that again. So the parabola, it's definitely a function. Can't say that my drawing went too well right there. It's a function, and the domain on a parabola is all reals. So you can also write this in set notation. Say something like the set of all x such that x belongs to the real numbers. That's also acceptable. I prefer the interval notation. Okay, in this one, we would have a vertical asymptote at 2 and another one at -2. I know it said to use the calculator, but I'm just practicing my skills, which we'll learn as the year goes along. I can also make, oh, that was interesting. I can also make a table and test x values to know what the y value is. If I test an x value into the function here and say I test -3, I'm going to get a negative y value. If I test 0, I'm going to get 0. If I test -1, I'll get a positive. If I test +1, I'll get a negative. So you can see it's switching locations at 0. If I test 3, I'm going to get a positive y value. So up until -2, my graph is all below the x-axis. That's telling me to go down here. If I substitute 0, I get 0. And then I've got a branch there and a branch there hugging the asymptote. And then on the other side of 2, I have all positive numbers using that sign chart. And then we can read the domain this way. So from -infinity to -2, then from -2 to +2, and lastly from +2 to infinity is our domain. Are you still with me? In this case, we want that value under there. We have an even root, so square root is an even root. We can't have any negatives under there. So solving that argument, when I divide by a negative, remember the rule to switch the inequality sign. And then I divide by -4. I'm sorry about that. So in this case, it is a function. It is a function, and the domain would be from -infinity to 3/4, including 3/4, because if we put a 3/4 right here, we get 0. And if you put 0 there, you get the square root of 3, which is about 1.7. If you put a -1 there, you got the square root of 7. I don't know how big the square root of 7 is. If you put a 2 in there, it's the square root of 11. So it's going off this way somehow. It's a curvy graph going that way. Okay. And like I said, you can take out the calculator and verify all of those things. Wow, my phone is really going crazy sitting next to me here. Whoop. Okay, in the next 2 examples, a couple of applications. Carrie is a sales clerk at Electronics Depot. She earns $275 as her base pay, plus $15 for each item sold. We want to express her salary, G of X, G, as a function of the number of units she sold. So she makes a base pay of $275 plus $15 for each item that she sells. And then what would her gross pay be if she sells 12 items? Well, that just means to evaluate using our function notation. 15 times 12. So Terry is going to earn $275 plus what's 15 times 12? Is that 180? So $455. If Terry sells 12 items at the store, she'll be paid $455. If your pre-calculus book is dropped from a height of 25 meters on our imaginary planet Newton, its height in meters after t seconds is approximated by 25 minus 12t squared. How long does it take for the book to hit the surface of the planet? Well, let's think about that. To hit the surface of the planet, we would want that to be 0, because I'm dropping the book from 25 meters and it's going down a half of a parabola, since we only consider positive time here. So I'm thinking about, when is that time? What time is that where that book hits the planet? So since they both represent h of t, let's solve the function. for 0. So moving the 25 and the 12t squared to isolate those, we would have t squared is 25 over 12, and t is, like I said, I only want to consider positive t, so I don't need plus and minus. T is 25 over 12, and on my calculator, that looks like at about 1.443 seconds on the planet Newton, your textbook would hit the ground. I hope you understand. See you next time.